Here we're going to talk about the concept of real power. You have something called real power. You might imagine there's something called imaginary power, and we'll talk about that later on. But first we're going to focus on real power, and we'll be talking about, in this section, we'll be talking about resistors. So first, I'm going to leave this on the board probably throughout the next several lessons. I told you it was important. This is the instantaneous power. This means at any given moment of time, you put the time t in here, and then boom, you've calculated how many power, how many watts that the load is absorbing if it's a resistive network. And it's changing all the time. Now it looks ugly, but the reason we're doing it is because really what we want to do is we want to start talking about that, the concept of average power. All right, so we'll talk about average power, and we talked about that in the last section, capital P. And we said that it was 1 over t times the integral over a period. So we'll say t naught plus some period of time t, which is the period of the waveform, integrating the instantaneous power over time. We talked about this concept at great length in the last section. So we're going to integrate that. Now, obviously, the initial function of p here, we could have stuck it in there, but it's kind of hard to integrate that. So whenever you look at the expanded, full-blown version of it, you have this entire gargantuan thing stuck in there, and you try to integrate it. And first you look at it and you say, you're crazy. But then you start really studying it and start thinking about it, okay? Well, what's going to happen is you're going to be integrating the first term. We'll get back to that in a second. Plus, you'll be integrating the second term. Minus, you'll be integrating the third term. So really you have three integrals. You have integral over this term, integral over this term, integral over this term, right? That's how integrals work. You can integrate each individual term by itself. But then you start looking at this very carefully and realize that, hey, wait a minute, this is just a number, it's a constant. This cosine theta v minus theta I, theta v, theta I, they're constants. The phase angles are locked in depending on whatever circuit you have. They don't change. Unless you start monkeying around with the source frequency or something like that, or the components of the circuit you have, the capacitors and inductors. Once you lock down the circuit, theta v minus theta I as a relative difference in phase between voltage and current, that doesn't change, right? So this is just a number. This cosine here, this boils down to a number. Same thing with this last term. All of this stuff right here is just a number. It could be 5, or it could be 7, or something like that. So really what you're integrating in this term really is this. But look at what this is. You're just integrating a regular old cosine function. Now the only difference is you have a 2 here, right? Pretend the 2 wasn't there. You would be integrating cosine omega t, and you would be integrating that cosine over one period. Remember, t, the period, comes from whatever the frequency was defined to be to begin with. So you have some frequency going on, and then you choose to integrate over one period, right? So you integrate a cosine, it goes up to a maximum, down to a negative maximum, and then back up. You integrate over a period. If the 2 wasn't here, you would integrate this, and this integral would come to 0, right? But there is a 2 there. How does that change it? Well, all that means is the frequency is now doubled. I'm still integrating over the original period, but I've doubled the frequency inside. No matter how you look at it, the curve still comes back to its starting point over one period. The frequency is doubled, but I'm integrating over the original period. So it's a little faster inside, but it still comes back to its starting point. So I integrate all that stuff, and this integral of this cosine 2 times omega t over one period, it goes to 0. So this entire term drops away, and you would never see that if you were looking at the original formula for instantaneous power that we wrote down. You wouldn't see that kind of thing. But you can see it here when you start examining this. So then, this integral drops out to 0. This goes away, right, when you do this. Now let's look at this. This is exactly the same situation. This is a number. This is a number. Remember, sine of these phase angle differences, it's just a number. Then you're integrating the sine over the same thing. You're integrating it over a period. The frequency is doubled, that is true, but you're integrating over a period. So no matter where you start, the frequency is twice as much, but then you're integrating over a period, so it still ends up exactly where it starts. There's as much positive above the axis as there is negative below. And so you integrate it all up, and then you divide. So when you're doing the integrals, some is positive, some is negative, and the whole thing drops to 0. So this term, when you integrate it, goes to 0 because you're integrating over a period. This term drops to 0 when you integrate it. And this means no matter what is in the box, whether it's inductors or capacitors or whatever, these integrals of these terms always go to 0. Always, because you're always integrating a sinusoid over a period, right? So the reason we did all of that all of that work expanding that thing with the trig identities is because when we integrate it to find what we call average power, these last two terms drop away when we're calculating average power. The average doesn't come from these. It only comes from this one. This first term does not drop to 0. So what you basically figure out is the average power, capital P, is equal to the integral of this guy. Now, instead of writing it all down, let's think about this one just like we thought about these. We'll do a little thought experiment, okay? So this stuff here is a constant. This stuff here is also a constant. Cosine of a phase angle difference is just a constant. So this whole thing is a constant. What happens when you integrate a constant, right? Think about back to calculus. So this P here is basically, when we're talking about this first term, it's just a constant. So it can come out of the integral, and then you integrate over dt. And so you integrate dt, and you put the limits of integration in, and you divide. Basically what's going to happen is everything goes away, and what you're left with is what you started with. So when you integrate this stuff over a period, then you're going to evaluate the limits of integrations, do the subtraction, divide by t. Basically everything drops away, and you're left with what you have here. So the capital P that you get is basically Vm, is basically this first term, Vm times Im over 2 times the cosine of theta v minus theta I. Now, I didn't show all of that because I know you guys have taken Calculus 1 a long time ago, but do it. Stick it in there and realize it's just a constant. Then take the P out, right, and treat it as a constant, and do an integration, just integral dt. You're going to get t, right? Then you evaluate the upper limit of integration minus the lower limit of integration. The t naughts are going to subtract away. You're going to be left with capital T after you've done the integration. But then capital T divided by capital T on the outside goes away, gives you 1. So the only thing you have left is what you stuck in there to begin with, right? And when you think about it, that makes sense because we're saying this is an average. These terms drop away. This is a constant. It's a flat line constant. What do you think is going to happen if you try to average a flat line constant? It's not moving. This isn't wiggling at all. There's no up and down. This cosine is the cosine of a number. So it's a constant. So this whole entire term is just a constant. So you have a flat line constant. You try to take the average of it. What should you get? You should get that number. That if I have, what is the average of 5? Forever and ever, 5 is just going along, 5, 5, 5, 5 along along the instantaneous power is 5. What is the average of that? It's 5. So whatever you get, this is just a number. When you average it, you should get what you started with. And that makes sense. And that falls out of the integration and how it all falls apart, or how it all cancels out later on. That is why we took the time to blow this out, because you could see these terms go to 0. They don't contribute anything for the average, and the average power is just equal to this first term that we have. So I'm going to kind of circle this, or kind of put a little asterisk by it, because it's important. Let me make sure I said everything here. This is the average power over one period, so I will just say this is the average power over one period. Okay? And P of t, or little p, represents the instantaneous guy. This represents the average. And that's, I've already said that many, many times. All right, now, let's talk about what this all means in terms of resistive networks. We're going to get to capacitors and inductors later. They require a little bit more thinking. But for resistors, we can do an awful lot. Now, we drew a picture. I'm going to draw it really, really quickly before. We drew a picture before. This is time, and this is I. So we're going to say, let's talk about resistive network again. In the next section, we'll talk about capacitors and inductors. But here we're talking about resistors. What does the current look like for a resistor? We said the current is going to go down, it's going to go up, it's going to go down, and so on. Okay, and then we drew some dotted lines. We drew some dotted lines. We did this several sections ago. We drew some dotted lines. Okay, I'm going to try to do this quick because I know you've seen it already. And we're going to go here. What does the voltage look like? Whenever you have a resistive network, the voltage and the current track each other. They're in phase with each other. So the voltage is going to look exactly the same, or the same shape. It's going to go down here, up, down here, and so on. So these are in phase with one another. And so then the power that you get, instantaneous power, this is just review, little p is IV. So let me extend these guys down like this. So we did this kind of graphically before, and I'm going to show you that what we did graphically matches up with what we just calculated, or what we just figured out. So when we have something like this, what we said was the power starts out at a maximum. We're multiplying these two together. Starts out as a maximum, then it goes and bottoms out here, and then it goes back to a maximum here, and it bottoms out here, and goes back to a maximum here, and bottoms out here. And we talked at great length that when you have a resistive network, instantaneous power is always positive. It's always changing, but it's always positive. It never ever goes negative because resistors cannot store energy. So you can't have negative power in a resistor. It can never supply energy to the circuit, so it's always going to dissipate. It's always going to be a positive power absorbed by the resistor, or you can think of the resistor dissipating the energy like that. Okay, but I want to show you a couple things that you may not have realized. Okay, this is the kind of the original frequency. You can kind of see roughly how that goes. The power, because of the nature of the multiplication, doubles the frequency. So you see how it goes down and up, and we've only gone a half cycle here, and then it goes down and up, and here we've gone to a full cycle. So for one full cycle of the voltage or the current, the power has done 2 cycles. That means that the frequency of that instantaneous power is twice that of the frequency of the original voltage or the current. And that comes because this is the full-blown glory of the instantaneous power. This number is just a constant, right? But these guys here have cosine of 2 omega t and sine of 2 omega t. You have a doubling of the frequency. This all comes back from the trig identities we used a long time ago to blow it out. And this is another reason why we're doing it, so you can see these terms. So the doubling of the frequency of the instantaneous power comes directly, this is a plot of this function. If you stuck everything in and plotted it, it would look like this. And the doubling of the frequency is coming from these terms at the end. These are all constants, as we have talked about before. So I want you to keep this in the back of your mind that for a resistive network, this is what the instantaneous power looks like. Now let's shift our attention back to what we had here. This is the instantaneous power. We integrate it over a period, and this is what we end up with. But if you notice, this term is this term. Furthermore, this term is this term. So they're very, very similar. So actually, we can rewrite the instantaneous power using the result that we've calculated here. So we'll say little p, we can rewrite the instantaneous power as, because now we have what we call the average power. So we can rewrite the instantaneous power, and this might blow your mind a little bit, but we can rewrite it as follows. This term is exactly the same as this term. So we can rewrite instantaneous power as capital P plus this term is exactly the same as the very first part of this term. So we can rewrite it as capital P times the cosine, capital P times the cosine of 2 omega t that comes from here, okay? And then we look over here for a resistive network. Remember, we're only talking about resistive networks. We can rewrite the instantaneous power for purely resistive network. Let me write it down. For purely resistive load. We're only talking about resistive loads here. Things get more complicated when we have capacitors. For resistive loads, it's the average power plus the average power times the cosine, and then this third term, think about it, drops away, because for resistive networks, theta v minus theta I, the difference in phase angles is 0. Sine of 0 is 0. So this third term completely drops away when you have resistive networks. So it doesn't even apply. So the instantaneous power for resistive loads can be written as this, as the average power plus the average power times a cosine. Okay, so let me kind of circle that here, and this is something you'll see a lot. This is for, this is average power. I guess I'll write that as average power, and then of course this P is average power, like this. For purely resistive load. In fact, it's so important, I'm going to write it again. This is resistive load. All right, so what we're saying is this ugly equation that gives us the instantaneous power, all right? When you have a resistive load, can be rewritten as the average power absorbed by that resistor plus the average power absorbed times the cosine. Now, if you were to plot this, what would this look like? Okay, so we're going to plot this instantaneous power as a function of time. What do you think it would look like? Okay, well, we have two components. We have a constant, And then we have this other stuff. What would happen if we cover up the constant? This is just p, it's a number, times a cosine. So we know that cosines go up and down and up and down, and this is the amplitude, so it goes up to positive p and down to negative p, positive p, negative p, over and over, and the frequency is given by here, so it's double the frequency, but it goes up to p and down to negative p. But, so if we were to do that, we would start here, it would go up to p, down to negative p, up to p, down to negative p, up to p, down to negative p, but we're adding to that p. So really, I know this kind of gets a little weird, but this guy right here, this number is capital P, so we can kind of draw a dotted line here. And what's going to happen is you're still going to go, you're going to start from this number. You're going to go up to P and down to negative P, up to P and down to negative P. But since you've added this bias to it, you've shifted the whole curve up so that it's always positive like this. And I'll write this down for a third time. This is for resistive load. Why are we doing this? Because this looks exactly like this, what I've drawn before, right? So I'm showing you two different ways of thinking of the same thing. We're saying, hey, if you start from voltage and current and write them down in phase, because resistors mean things are in phase, and then you multiply them, you get a doubling of the frequency, you get a constantly changing sinusoidal function that always is positive. It dips down to 0, but it never goes negative, because resistors can never supply power or store energy. They're always going to dissipate stuff. So we have positive power always, and it looks like a sinusoid would double the frequency of the original frequencies we have. This was just a graphical approach. Then we turn around and say, this is really the equation for instantaneous power, right? And then when we do some derivations and define what average power really is, then we rewrite that instantaneous power as average power plus average power times a cosine. When you plot that, it looks exactly like what we got over there for a resistive load. We start at a number P, we go and we superimpose onto it a cosine that goes up P. Remember, this is P up, and this is adding P up here, and this is subtracting P, giving us going down to 0 here. The frequency you can't see so much here because I don't have any other curves stacked, but the frequency is twice that of the initial frequency here. So this is the thing that you want to pull out here, basically, is that the average, so if you look at the instantaneous power, this is the instantaneous power of the resistor. Look at what's right in the middle. Here's the hill, here is the valley. What is right here in the middle? It is capital P. This is the average power. So what this is basically saying, if I told you over here, if I said, hey, this is what the power is doing in a resistor, what's the average power? You probably would go and point here and say, well, half the time it's higher, half the time it's lower, so right here in the middle, this should be the average power. Well, that's all we're saying here. We're saying this is the average power dissipated in a resistor. Average power is given by this equation right here. This is the average power. Sometimes the power is absorbed or dissipated a little bit more than that when the voltage and current is higher. Sometimes the power that's absorbed or dissipated by that resistor is lower than that, sometimes even going all the way to 0. But on the whole, looking over multiple cycles and looking at the whole thing, half the time it spins higher than P, half the time it spins lower than P. So on average, the average power dissipated by the resistor is capital P, which we have defined to be right here. This is the average power. All right, I think I've said everything I want to say. I want to write one more thing down over here. So these are important terms. Now we have a little more explaining under our belt. We know that little p is called the instantaneous power. But now we're going to change it a little bit because eventually we're going to start talking about inductors and things. So we're going to change this. This is the little p is called the instantaneous real power. Okay? And then we have something called capital P, which we're just going to call real power. And we also can call that average power. Now, we have real power. Eventually, we're going to get, there's going to be something called Q. That's going to be kind of imaginary power. That's going to be the power that's associated with the sloshing around of the inductors and the capacitors and the fields that we talked about in there. But for now, everything's real. So we have the instantaneous real power, and then we just call it real power, or sometimes you see it as average power, but we're going to generally talk about it as real power. Real average power is what capital P is. And when we have real power, when we have the word real in front, I'm just going to read this, I'm not going to write it down, but this is very important for you. Real power is transferred from electrical to non-electrical form, usually like heat, right? through resistors. You cannot get that power back. So when you see the term real power, don't think of it as weird or mystical because imaginary power's out there and we haven't talked about that. Real power is just stuff that is in the real world that gets dissipated. It's lost. It's lost power. You could almost call this lost power. Power that you never get back. Power from heating up a toaster, right? The current goes into the toaster coils, it heats up, the energy goes away and you do not get it back. It's lost from the system, right? That's called real power. So the instantaneous real power is just the instantaneous value of that. It's always going to be there and it's instantaneous. And then you have something called, we just call it real power, or the average real power is basically the average of that quantity over time. And as we've seen for resistors, the average of that number is easily calculated. It's just a number. It's the voltage maximum times the current maximum over 2 times the cosine of the difference in the phase angle, right? Now, if the phase angle, think about this, which we haven't gotten to yet. If the phase angle really is 0, the difference between these guys, if it's a resistive load, the difference here is 0. So cosine of 0 is 1. So for resistive load, this actually goes to 1. Right? So that means the power dissipated, the average power dissipated is VI over 2, or 1/2 V times I. And you can see that down here in this plot. This is the maximum here. When V and I are multiplied together, this is the maximum that you can have. You take half of that, you end up right here. So it's just saying the same thing. Some of it's in graphical form, some of it's not, but that's the basic idea. I need you to make sure you understand this stuff because we're going to be picking apart these terms and then moving on into how to analyze this for inductors and capacitors, and we'll solve some real problems. We have to get kind of through a few things. So I want to real quickly recap. We had the concept of instantaneous power. You just multiply the current and voltage together. We used a bunch of trig identities to blow it out into 3 terms. We want to try to figure out and learn as much about it as we can. So we want to define something called the average power. We integrate this term over a period. But when we do that, we figure out that this term drops away and this term drops away. So really, the average power over one period is just the first term here. And this is true no matter what your load is. We haven't talked about the load being resistive or anything like that yet. So no matter what your load is, these terms drop away when you're calculating averages, right? This is the only one that is non-zero. So this is the average power there that you have no matter what. You plug in the phase angles, you take cosine, multiply here, boom, you get an average power. Now we start talking about what happens if you have a purely resistive load. We're going to take 3 cases. First case is purely resistive load. Then we'll have purely inductive load. Then we'll have purely capacitive load. And then we'll talk about when you have a mixture of all 3, which is going to be easy to understand once you isolate them. So for the purely resistive load, you look back at the equation and say, well, wait a minute, purely resistive load, then the instantaneous power is P, which is this average. This looks just like the average power, so we just say it and put it in there. And then this can be called P times the cosine there. But then for resistive loads, this will be 0. Theta V minus theta I will be 0, sine of 0, 0. So this third term drops away whenever we're just trying to find the instantaneous power for resistive load. So we can rewrite it just for visualization. This is really the equation, but for visualization purposes, this is kind of cool because for a resistive load, we say that it's capital P, average power, plus average power times a cosine. When you plot that, you get a cosine function that's shifted up above in the positive direction here, in the positive power direction, and it goes above and below where the middle point here is what we call the average power to begin with. So if somebody gives you a problem and says, hey, here's a voltage and a current, and it's a resistive load, calculate the average power. Well, if you know what the difference in the phase angles are, and you know what the amplitudes are, boom, you have it. And if you know it's resistive, you know this thing is going to be floating above the axis like this, going up and down, sometimes dissipating more power, sometimes dissipating less power, but on average, it's going to be dissipating this much power right here. And this other stuff we did was just kind of talking from first principles back in the previous section. When you take voltage times current, you get this. This is just showing you that when you multiply voltage times current, you get exactly what the equations predict that you should get. So what you get is an average power where the instantaneous goes above and below. The average is right through the middle there of that cosine. I think that's about as much as I can say about it. I'm repeating myself a lot. I know I am. It's because it's really important. I want you to get in the habit of thinking about instantaneous real power for a resistor being up above the axis like this. and then later on I'll draw some pictures for inductors and capacitances, and then we'll put it all together. So follow me on to the next section, and we'll get there one step at a time. Learn anything at mathandscience.com.